I get there, I wanted to go through some of the main pollutants that I'll be talking about today and what kind of effects they might have on water quality. I'm assuming that some of this might be background, but I just wanted, if I'm going to throw around the word sediment, I wanted to make sure we're all on the same page. Sediments in Hawaii come obviously from natural erosion processes. We have beautiful deep gulches that have for millions of years had sediments running into the ocean, but there are also human and ungulate-induced problems. It's not just humans, but also animal-induced problems that come from, that can cause excess sediments, which lead to reduced light, changing stream habitats, and coral mortality in our coastal and stream waters. And we also have nutrient contamination. So nutrients, nitrogen and phosphorus are the main culprits here, are essential for most aquatic ecosystems. But if you have too much nutrients, right, up to a certain point, nutrients are what organisms need to grow. But up to a certain point, you can develop an overgrowth of macroalgae, and that can be detrimental to corals and turtles and other organisms. And this picture is actually pretty recent from Kahikili on Maui, showing what an algae overbloom can look like. And just so that we're all on the same page for water quality, I know we've talked a lot about kind of infrastructure that you can use to kind of mitigate some problems with water quality. But when I think about water quality, I think about water quality for a specific purpose. And so the water quality that you need for drinking water is different than the water quality that you would need for your stream. It's different than the water quality that you would see in Kona versus the water quality in Hilo. And so all of those different designations for the Department of Health actually has different standards for each of those types of designations. And so water quality then is a relative term, right? It's relative to what organism or to what parameter you're thinking about. And I list some of them here, some of the different ways that the Department of Health, the State Department of Health defines water quality. There are limits for pH, salinity, dissolved oxygen, and temperature. So for instance, if all of a sudden we wanted to have some sort of plant that used cold water and they want to discharge excess heat back into the ocean, you actually can't really do that if your water quality, if your temperature is exceeding, that could even be a water quality parameter, temperature. Turbidity, so how clear is the water? Are there harmful bacteria in the water? And then are there too many nutrients, which are they talked about for the whole nitrogen cycle there. And just a little bit of policy here. The Department of Health is funded mostly for coastal work, for coastal water quality by the Beach Act. And the Beach Act really is in charge of trying to protect people from recreation users from getting sick on the most used beaches. And so while they also will measure for nutrients and worry about ecosystem effects, the Department of Health is really tasked with human health. And so will most often measure for enterococcus, which is an indicator of sewage or wastewater problems, both from humans and from animals. So just to make that clear, when the Department of Health has their priority list, they're usually tackling beaches or places that a lot of people go to and that might also, so a lot of people is the key, and bacteria is the main indicator parameter that they're concerned about. So here's just an example from state water quality standards from coastal water quality. I don't expect you to really be interested in this. It's just HAR 54 is where this is derived from. And so if you want to see what those standards are, HAR 54 is where to go. I think it's 11-54. So you can go and look it up, and the real standards are there, and they're actually, you have to put them into tables like this to try to understand them. So another kind of key concept here is point source pollution versus non-point source pollution. And again, I just wanted to make sure that we had those kind of basics within us before I talked about kind of how the methods go. So for point source pollution in Hawaii, usually that's considered wastewater or industrial waste, and we don't have as much industrial waste here. So for Hawaii, when I think of point source pollution, I'm usually thinking about wastewater discharges. In 2015, for instance, 50,000 gallons of wastewater were discharged in Waikiki in a single instance. And so when I think about going into a watershed and thinking about green infrastructure options, most of the time I'm not thinking about point source pollution, because point source pollution in some ways is really easy to solve. You've reduced the source, right? It's like one place. A lot of green infrastructure is meant to design to try to capture non-point source pollution. So non-point source pollution comes from many places. It comes from the runoff on your roof. It comes from agricultural land runoff. It can include all kinds of pollutants, sediments, herbicides, oils. It's a big mixture, and it's diffuse. It's a diffuse problem. And so in order to solve a diffuse problem, you need a diffuse solution, which often is where infrastructure that can handle a diffuse problem is needed. So what are the threats? By different parameters have different things that cause them, right? And I talked about sediments already a little bit in terms of humans and ungulates. Well, for sediments, ungulates like goats and cattle and deer are kind of just secondary in some ways because they eat the vegetation that's holding the soil back. So ungulates, by eating vegetation off of Kaho'olawe, have created excess sediment runoff because there's nothing left to hold on to the sediments. In Hawaii, old agricultural roads often can create problems when they're on steep slopes and not maintained. Throughout the tropics, trails are usually identified as a major source of sediments. When I've been hiking in the back of Waimanalo, most of the sediments I see are running down the trails. They're coming from everywhere, but you can note that the places that have hard surfaces are sort of the worst. And then shoreline erosion I'm putting on here because as sea level rise becomes a bigger concern, there are definitely places that are more impacted by waves coming up and cutting into the soil layers that aren't really sandy, and that actually becoming a source of sediment. So shoreline erosion is increasingly becoming a source of sediment in the coastal zone. For nutrients, golf courses and landscaping, and then together nutrients and bacteria, cesspools. I think Lauren mentioned in an earlier seminar that there are 100,000 plus cesspools left over in Hawaii. And cesspools are pits. They're basically sewage pits that aren't really expected to be processed all that much. So there's really no extra, the sludge is not removed from a cesspool, it's just incorporated into the soil itself. And then oil and heavy metals from roadways. And so things like green infrastructure can try to address oils and heavy metals by giving as a retention basin, either a wet or a dry retention basin, as a place to concentrate that excess runoff before it runs into the groundwater or the stream system. So I'm going to highlight just a couple of those threats and how you can think about them. Golf courses are often a big threat for the coastal zone because they're right next to the coast. So people like to golf with a view of the ocean, and that's particularly true here in Hawaii. And then the fertilizer rates that are needed on those golf courses, sometimes they come from recycled wastewater, but often are fertilized at rates that are much, much higher than you would say fertilize your backyard. And so that can become a possible concern if you're worried about excess nutrients in the coastal groundwater and coastal water system. And then I mentioned cesspools, but I don't think we had an image last time of what those cesspools look like. All those little orange dots represent all of the different cesspools on Maui right now. So you can see a lot of upcountry, a lot of Kahului. There's a lot of them out there. And also on this map, I have the red and green, the bigger dots are the Department of Health water quality data. Summarize the geomean of that data showing, but you can see that the Department of Health data doesn't nearly cover the area, like all of the coastal water, right? It's really spatially limited right now to West Maui and a couple of sites in Kihei. So that's kind of, if you want to see where you might have a nutrient problem, this is one possible place of where that's coming from. Okay, so how to prioritize sites for green infrastructure. Like how would if I only have a limited amount of money to install retention basins or to put in green roofs or to do any of the pretty neat, more modern types of infrastructure improvements that you can do. On agricultural roads, you can put in water bars that slow water down. For stream systems, you can put in geotextiles on the banks of the streams that prevent excess sediment from getting into the ocean. But somehow, often when I work with communities, I'm asked, okay, what do we address first and how do we address it, right? That combination of questions becomes pretty difficult. And so you have to start somewhere. And the 3M model was given to me by my friend John Stock at the USGS. This is totally his, I'm totally adopting his structure for the 3 M's of mapping, monitoring, and modeling. And I still use this when I think about a project as well, as the 3 ways that you can address the problem. By mapping, you can get a summary of all of the data that currently exists and often perform calculations to try to extrapolate and visualize the data. Even the map I presented of the cesspools just 2 maps ago is a lot to provide for decision makers to say, maybe you need to look and make sure that if you're taking your your drinking water from upcountry Maui, that you have enough, that you're not exceeding nitrate limits up there since there's so many cesspools in the vicinity. So sometimes even simply mapping a parameter might be enough. You don't have to come up with some crazy model if you're gonna first map the problem out and try to use that to kind of identify places that might be problematic. What helps with that is that we right now have, how many of you have used CCAP data in any of your work? Okay, a couple of you. So CCAP, I don't have it here, but CCAP, the coastal, I'm gonna lose my initials. Sorry, can't do it. CCAP, the CCAP program is a program by NOAA that maps land use to satellite imagery, worldview imagery. It's very fine imagery down to 2.4 meters that shows land use. And then they take those images every 3 to 4 years and process them and make them publicly available. So you can download data off of the NOAA website that gets you land use down to 2.4 meters. And having such a fine resolution of change and to see how things are changing over time really allows you to make manipulations. So if you're really looking at a watershed, you could just start by looking at what that looks like. You'll be able to see the erosional surfaces. You'll be able to see different aspects of the watershed that way. The next is monitoring. So an investigation at a point in time or over time. So sometimes mapping can only get you to see the spatial, but it can't actually tell you what the nitrate levels are in the coastal environment at all, right? No amount of mapping can get you there. And so you actually have to go out and take a water sample and analyze that water sample. But one water sample is not enough, so you got to do it. And you got to do it again and again and again, so you get a good average and a robust sample set. The Department of Health is tasked with doing that to some extent, but like I say, their funding is mostly focused on enterococcus right now. So if you're interested in nitrogen or interested in sediments, you might not get a good data set over time. And the last is modeling. And I know there's a lot of great professors around here that are working on modeling techniques. And modeling techniques can allow you to look at sediment and nutrient export over in a way that takes those land use maps and tries to assign approximate values. So for instance, for golf courses, if you know that it's producing 200 kilograms per hectare of fertilizer use, you could actually use a model to try to estimate how much of that nitrogen then ends up into the stream or into the groundwater. So it's one way to use a model, right? Another type of, so what those options look like are, you can have real world data like the Department of Health here. And this is the spatial limitation of that data, right? It doesn't show you everywhere. So if you look, you can see all these orange, these green and red dots are all of the data over time. So Oahu is overrepresented with samples, whereas if you really want to know what's happening in Kahu, you're not going to get any response from Kahu because people don't swim there enough in the Department of Health to pay attention that finely. So it depends on where you are. There's no data from Lanai, there's no data from Molokai right now. So you can use real data and you can try to find data sets that help you understand what your problem looks like. You can use modeling approaches. So one of those modeling approaches is a tool set called INVEST. And INVEST was designed for ecosystem services. But within INVEST, you have sediment and nitrogen models that can help you predict what sediment and nutrient export might look like. And on the left is a map of West Maui showing nitrogen export. So you can actually predict spatially where you think nitrogen is coming from based on different land use types. Or you can use another type of model called the stormwater management model, SWIM. And this is the EPA gold standard for being able to produce, to estimate where runoff is happening. So there are modeling approaches, right? This is the modeling piece of what you actually do to kind of look at this. And then the mapping approach, I want to highlight the work of Ocean Tipping Points here. Ocean Tipping Points is a big project that tries to look at different ocean human indicators that try to push the ocean into one state or the other. So this is part of a huge project, but this particular map, which you can download online, is total effluent, which takes all of the cesspools and then estimates what the effect of those cesspools would be on the coastal environment, right? So there's already people that have done this, and you can download that map for the entire state right now to estimate this. And this map was produced by Joey Leckie and the Olson Lab. So that's the credit for that. But similarly to this kind of mapping tools, there's already a lot of maps out there. So if you're interested in a particular watershed, you can go and try to overlay some of these images without even having to kind of go back to the base layers yourself. So that's kind of the big picture, right? So you can map it, you can model it, or you can monitor. So in the 3 case studies and 3 places I'm going to talk about today, the first is West Maui and a water quality sampling project where you try to get more monitoring data. The second is Lanikai, where I was mapping, monitoring, and modeling at the same time. And the last is a stormwater model that the EPA uses, that I used in a case study in Honolulu to show you how you can do this in your own backyard on a tiny TMK, on just a tiny property. So I showed you that big map of the Department of Health data, right? The one with all the green dots overlaid with the red dots, the one that had a whole lot of points on Oahu, that map. Well, there weren't enough points in West Maui for people to make good decisions as to where to repair things, right? Do I pick cesspools here, or do I pick aggregates here? And you can model it. I showed you that model, right? You can model it, but people weren't sure if the model was correct. And so the community really wanted solid data to try to solve the problem that you see in this picture, this huge brown water plumes, which are happening over and over and over again in places like Honolua and Honokokua. So there's big brown water events that are happening, and the community wanted to engage, but there was only one guy in the department, one guy named Roland, and he was awesome. And he was sampling all 70 sites in Maui, and he was prioritizing the Enterocockus sites. So even though he tried to help, Roland couldn't help enough, right, to kind of really understand what that data looked like. And so he's now retired, so he doesn't have to do it anymore. And he doesn't have to do it anymore because Maui residents really stood up and were like, we want to do this ourselves. And this is a picture of us playing turbidity in the coastal zone. I think this is Dana Reed's husband, Bill. And so a group came together. These are the core volunteers, the initial core volunteers called Huia Kawaiola. And Huia Kawaiola went through and they wrote standards that match the Department of Health and take samples exactly like the Department of Health takes samples. And they formed a community organization to basically collect the data themselves and using those Department of Health standards. And so now, because they have a document, this fancy document is called a QAP, and many of you have heard me probably talk about the QAP before, QAPP. If you write a QAP, which is essentially just a cookbook to how to take your samples and what you're gonna do with that data, if you have a QAP that's approved by the Department of Health, then your data can go into the EPA data system and be used to make regulatory decisions about water quality in there. And that might help to fund county efforts, city and county efforts, or to repair or fix some of the infrastructure that might be causing said problems. So the result of this, and the website's huiokawaiola.com if you want to see the full picture, if you want to download the QAP, if you want to look at all of the data, all of it's available. But in the process, we set up a lab, and in the end, the full picture looks like this. Instead of just having some dots, now we have a full picture of data going up from Honolulu all the way down to Papalao down here. And then the County of Maui has just funded an additional 24 sites to Maui Nui Resource Council to fund all of Kihei down to Ahihiki now. So this program is expanding, but it's one technique, right? It's one of those 3 pieces of how do I know where to fix? Well, I take coastal water quality data. And in our case, there's some big red dots up here, and there are places that have both cesspool and golf course problems, right? And then you can use this data to go back and verify those models. So you can then look at places that might not have as good data. So they kind of work together a little bit. Okay, so that's case study number 1. This might look simple, but I could talk about it for an hour. It took a very long time to form this group, but you can get community members and academics to sample your water quality for you, and that can help point out where the problem is. Okay, so option 2, in Lanikai, Oahu, Nature Conservancy was approached by the Lanikai Association to look at coastal water quality. The first round of this was looking at benthic fish surveys, and it was noted during the fish surveys that there was a lot of sediment on the reef, and it was suggested that it was a possible cause, that there was a possible water quality issue in Lanikai. And so the community association was like, hey, TNC, can you look at this problem for us and see where you think those sediments and nutrients might be coming from? Do we have a water quality problem? So this is Lanikai. Lanikai is beautiful as ever. Most people don't think of water quality problems when they think of Lanikai. It's got traditionally pretty clear water that most people love to swim in. When I look at Lanikai, this is the CCAP data. I see a lot of residential homes with some amount of impervious surface with no real golf courses except for this guy here, which kind of splits its runoff between Lanikai and Enchanted Lakes around the back. I see a hill slope that doesn't have native plants, but is pretty vegetated anyway, so might not be a problem. I see a big fat trail that goes down to the coast that might be causing problems. And I see a whole lot of seawalls that look like they're kind of changing the way the oceanography is in that particular area and might be causing beach erosion at the same time. So those are the first things. The Department of Health had very, very, very little, even though they have a site in the database, they had very little data. And so we also looked at Kailua and Bellows and Waimanalo Beach, which had much longer data sets to just compare what the water quality would be to the two surrounding communities. And we kind of threw the kitchen sink at it, right? Lanikai is so small, it's not hard to throw the kitchen sink at it because it's so small. So we did kayak surveys to look at turbidity everywhere off the coast. It was a really hard job. Somebody has to do it, but spent a whole day kayaking around with the turbidity sensor. We went out there and we took water quality samples for turbidity, nutrients. We did bacteria sampling. So we actually measured things. That's the monitoring piece. We mapped out erosion. Let's see. So we tried really hard to catch storm events. I was a lot less successful than Andy Hood, who lives there. I live on the other side of the mountain, so by the time I got over there, it was already done. So there's some pretty pictures somewhere showing really big runoff events. Both of these channels can flow really, really big. But we looked and tried to find what the problem was. On the left picture there, you can see that's what the pillbox, the bottom of the pillbox is, if you haven't been up there in a while. It's just really strong evidence that erosion, like the sediments are just pouring down there during big rain events. And there's also some pretty big flooding problems that the residents were talking about regularly. And then the one last piece is we actually did some measurements on Lanikai Trail to see what the original surface would be, and then to do actually drop pin measurements to kind of figure out what the trail, how much trail loss there was. So kind of use cross sections to try to figure out how much erosion from the trail had happened over the last approximately 10 to 15 years. So we did that, and then we used some studies by, there were some coastal erosion estimates that we were able to use. Sorry, I'm blanking right now. But we were also able to estimate coastal erosion at the same time based on some previous work. So in addition to all of that, because it's so small, we used the INVEST models to estimate sediment and nutrients. And so this is what INVEST says. This is a kind of very tiny case study of what INVEST can do. For sediment, it kind of correctly identified that the ridge and the trails up here were most likely the causes of excess sediment in Lanikai, and was able to kind of say that there was some hill slope just being the sides of all the hills, not necessarily the channels, but the side of the hill, that there was some erosion possibility from up there. The nutrients, so we modeled the whole thing all the way out to Enchanted Lakes out here and the channel leading out to Kailua. Most of the nutrient was concentrated on landscaping at people's houses, estimated to be concentrated on people's houses and on the golf course, but the golf course generally all the nutrients wanted to go downslope the other way into the channel, not into Lanikai. And we compared all the historical Department of Health data that was there, right? Whatever Department of Health data they had, we looked at, and we found that while the turbidity was much higher then, so the red and the blue, the red is Lanikai and the blue is Kailua Beach. And while Kailua Beach had generally higher turbidity, Lanikai also had higher than the state standard, which is that red bar of 0.5. It's a very high bar to meet. It's really hard to get to 0.5 NTUs. But that both beaches showed problems, but that Lanikai generally had clearer water for the last 3 years. In our only one-time sampling bacteria testing, we found 2 samples that immediately exceeded the Department of Health standards for Enterococcus at both side ends of Lanikai, and this needs further data analysis to figure out why, but we did do that piece. And our kayaking survey showed that most of the turbidity was strongest inshore where the waves were breaking, which isn't a surprise, but that especially down where the seawalls were, the seawalls being on the lower side of the map here, that where the seawalls were correlated to higher turbidity in general, so that you could see that that relationship was there. So all of this information was sort of packaged together to say, okay, well, you have some places that are exceeding your bacteria limits in Lanikai. You have seawalls that look like they're contributing to possible higher turbidity in the coastal zone. And you have a trail, the Lanikai Pillbox trail, that looked like it was exporting, based on our estimates, about 100 tons of sediment per year from the trail alone. And then the work of Fletcher, so that's where the shoreline erosion models come from, showed about 32 tons per year sediment just from sea level rise and from beach cutting into the soils that are on the beach from Lanikai. So we estimated all this up to try to get to these 2 big circles here to try to show where the source of everything was, right? So now there's both a modeling, a mapping, and a monitoring piece as you combine all 3. And from the sediment side, the Pillbox Trail was contributing about 60% of the overall sediment, with shoreline erosion about 20, and then the hill slope, just the background erosion from that watershed, is about 20 as well. And so that's one way of looking at it. On the nitrogen side, we really didn't find that much of a problem, right? Both our nitrogen and our phosphorus levels were below the state standards on average. And so there wasn't as much nutrient pollution as, there wasn't anything that really was putting up red flags there. But we were able to try to put it together into these different categories. So that's kind of how a very small scale, Lanikai was small enough that you could do everything, right? Like, hi, I'm going to model and I'm going to go and I'm going to climb the pillboxes and I'm going to go do this kayaking. We were able to put all the different pieces together for a small watershed and to try to designate what the problem was. So now from a policy perspective, from a recommendations perspective, you can say, perhaps your priorities might want to be, and they don't have to be, but the Pillbox Trail does seem to be contributing to more sediments than other places, and that shoreline erosion seems to be increasing wave energy. And so here are 2 recommendations that might then correspond to different green infrastructure options. So that's kind of how the package gets put together. All right, how are we doing? So the last piece I wanted to show you before I ask for questions is a model called the EPA Stormwater Runoff Tool. And this tool, you can go to this website, and if you just type in National Stormwater Calculator, you can get there. I will accept that it might be a little bit simplistic, but what it can do so quickly is sort of beyond what I've seen any other tool able to do. So that model that I showed before, the SWIM, the Stormwater Management Model, the SWIM model from the EPA, this is the online version of what that SWIM would be. And so let's see, Melissa, if I escape out of the presentation, will the people be able to see the screen still? I'm sharing the exact screen. Okay. So in order to show you a little case study, because I had to pick a place, I actually haven't used this in my direct work, but more for my own house. And so I'm showing you a tool that I haven't yet used with a community. So take that with a grain of salt, right? Because I haven't done it like that. So I live right below Assets High School. And so I decided to use that as our case study for today, because I am the little house, the little white house down here is me. And this is Assets High School. And I live on a really steep hill slope. Like I live up like this on stilts. And so anytime it rains big, the effect of assets very directly affects runoff in my underneath. It goes just straight underneath my house because I live on a hill slope and my house is on stilts. And so I have a very, very personal relationship with the site. So I decided we might as well pick this site because it's fun and I needed a place to start. So I set up a little scenario. And so what the model allows you to do, let's see if I can do this. So hold on one second here. I set us up. So this is the model. You can download it as a desktop application as well. And then I'm going to open the save site here, and let's hopefully it'll go there. Okay, so you guys can see that it has overview and then all these little tabs on the top. Well, what the stormwater calculator does is it allows you to pick a single site and then go through and see all of the soil data for your neighborhood. It's retrieving the data. I hope the internet is fast enough. So I picked the Aleva site, right? That's my house, and that's the Aleva. This is Assets High School right here. And this is all of the soil survey data that it downloaded from the NRCS for my neighborhood. And it's considered that it's C moderately high for a runoff potential in my neighborhood. You can actually see where the cliff is. It's this big pink right here, and that the green is where it's flatland. And the yellow is considered moderately risky. And for soil drainage, then, if I click on the next tab and go to soil drainage, it also downloads all that data automatically for you from the NRCS. So you can see what the drainage rates are. And then topography, you can look at the slopes, and you can see Assets is perched on this nice little happy hill up there. And then I'm on the pink here, which involves my 90 stairs to get to my house. And precipitation. So it finds all of the active rain gauges in your neighborhood, and it allows you to pick which one you want to go to. So I picked number 2 because I know how rainy it is, and I figured this side of the valley would be closer to the traditional. So what is happening at number 2 here. And then it looks for evaporation. So it actually looks and finds the sites that have evaporation data in your neighborhood. And so I picked Waikiki mostly randomly because Lion Arboretum seemed like the wettest place on the planet compared to me, and I didn't want to go there. It has you do climate change scenarios, so you can think about whether it's going to be hot, dry in the future, or warm, wet, or no change. And if anybody wants to look into this, I'm not really sure what model it's based on. So if you ask me that question, I'm sorry, I don't know the answer to it, but it's probably easy to figure that out. And that goes through land cover. And then I think you have to set this yourself, whether it can do the analysis for impervious surface, but it can't tell you whether it's forest, meadow, lawn, or desert as the other percent. So it knows it's 60% impervious, but it doesn't know what everything else is. So
one of the resources is City and County does have a database on tree coverage.
Okay.
Which also includes your impervious surfaces, and they have done that so that you can take data from that
and put it in here. I just guessed based on looking up that it's lawn. Yeah, no, I mean, it seems like I didn't think of it as a meadow, that's for sure. And then so you run this once, and it gives you a baseline, and then the second time you run it, it runs this scenario, right? So you can pick what percent of your property do you want to try to implement these different green infrastructure options. So I suggested that poor Assets High School above me, that's the guinea pig in my thing today, gets 20% on rain gardens, 20% in green roofs, 20% infiltration basins, and a 40% permeable pavement because I know they have a big parking lot. So I was like, okay, let's try this out. And when it comes down to the results, let me show you back to here again, what this ends up looking like for the results, because I couldn't do everything live. I did my best. But it compares the baseline, which is no changes, with the current, which is those changes that I suggested, right? These scenarios where I added porous pavement, rain gardens, green roofs, and infiltration basins. So this is my current, this is what's called current in this weird language. So the current scenario is when you're trying to model all those green infrastructure options. And then the baseline scenario is this, the original, what it is right now. And so it goes through and it calculates what your average rainfall is, your average runoff, and then all these different types of parameters that can talk about the runoff on your property, right? Like what that rainfall might look like. Actually, don't mind me. I think the current is the 0 and the baseline. The one that has the worst possible situation is the nothing, and then the one with improvements is the I've added now infiltration basins and green roofs and things like that. But the cool part is it gives you capital cost estimates, and I realize that this is probably not, like, we probably have to modify this a little bit for Hawaii, but it gives you a baseline for starting if you're going to have a conversation with someone about how much is it going to cost in order to do this, right? In order to implement those rain gardens or those green roofs or something like that, it gives you an estimate of how much surface you would need to do that. So I thought that the fact that they tried to include cost estimates was really neat. And then it gives you these nice, this is all in the PDF that exports from this process, right? It gives you a combination of extreme events, right? What the return period is and what is percent runoff, what's percent rainfall, and how that can be reduced. So the impacts on the right here is extreme. So in a 15-year storm or a 30-year storm, if you don't include these best management practices, you will have this much more runoff in your situation. And on the left, it actually breaks down your data for your particular property, wherever you are, into what percentage infiltration do you have right now versus if you had a green roof, what percent evaporation, what percent runoff. I love playing with this tool, and I'm sad that I haven't actually needed to use it for a particular community, but it's operating on a TMK scale. So I think, you know, it could go as big or as small as you wanted to use it. I probably wouldn't use it for all of Lanikai, right? Because that would, I'm not going to put green roofs on every house in Lanikai, but would I consider putting it on a single house in Lanikai? Yes. Like for that type of scale, it might work, or to work with the golf course there on different types of infiltration basins and things like that. So again, the National Stormwater Calculator is the name of this particular tool. If you ever try to download SWIM, which is what this is based on, the stormwater management tool, it actually goes through and models runoff. SWIM is kind of a beast. Like, it takes a little bit of a learning curve. So the fact that there's this online tool to kind of simplify it really helps if you wanted to just do a quick and dirty analysis for a client to say, okay, if I put in this many infiltration basins on your property, I think we can improve the amount of runoff or increase infiltration by this much. So with that, I've finished. I wanted to finish in time to make sure we had discussion, since you guys have been asking so many good questions in the last time. So I think we have about 10 minutes for questions. Miss Leah Brown.
Can I have 2 questions? So you're defining green infrastructure based on these sort of the kind of engineering type solutions. You're not thinking about green infrastructure as being like forest restoration or things like that. Like, how are you defining green infrastructure?
It's a good question, and I kind of stumbled on it myself, because I was like, look, in some places like West Maui, removing ungulates from the forest is extremely important to being able to maintain a healthy forest. I'd love to hear from others on this, but in my head, green infrastructure really thinks about that kind of gray nuts and bolts engineering structure and turning it into something that can absorb the water better, right? That can reduce runoff, which in turn reduces pollution. That's sort of how I think about it, but I didn't really highlight here, but the restoration of our upper forest is probably the single best thing you can do to improve groundwater resources. And I don't know why I don't in my head associate that with green infrastructure, but it doesn't have that concreteness literally to it. So
if I could, if you look at US DOT and US EPA, both look at a hybrid of the hard infrastructure, and for 2 agencies, it goes into a hybrid of that. Where is that line between the hard is going to do things that needs to be done, but the better application is the greening of that infrastructure, and whether you do green roads, rain gardens and things of that sort, they all do have that natural systems component to it. Go up to Makiki here and take a look at the green machine, and that is a piece of green infrastructure. These are just, it's a hard piece, but it has that natural systems component to it. And that's why most, at least the federal level, it's looked at as being a hybrid system, because it takes both pieces. It takes some human engineering to recreate those natural systems process in our built environment.
Yeah, I think it just gets talked about in different ways in different circles.
I got a little lost. Yeah.
Can we have a request from online that if you
Okay.
can repeat the
Yes,
question?
thank you for
And
reminding
just
me.
remember that anything that's mentioned out here, the 12 or so people online aren't able to hear. So if
Okay.
you're able to repeat a quick summary of that information.
I know it's hard to reproduce you. The question was, what do I consider green infrastructure, right? Or how am I interpreting green infrastructure for this particular application? And the answer was that there's a fine balance between how the EPA, the federal agencies, think about restoring kind of the natural system versus the built environment and turning it into a more natural system. Is that a good summary? Okay, there you go. Question.
What would be your candidate on a lot, the best choice, the highest priority choice for stormwater capture to avoid the greatest runoff?
Do you mean in terms of where, which
Yes.
watershed?
Well, not this watershed, anywhere in the island where if you could do stormwater capture, you would have the largest impact on reducing sediment loading.
Sorry.
I'm sorry, if you can repeat the question.
Yeah. Hold on. So give me a second. I have a lot of maps in my head. The question was, if I could implement stormwater runoff best management practices, stormwater capture, anywhere on Oahu, where would I do it to have the largest impact? Again, I would break it down probably by the constituents, whether it's sediment or nutrients, and I'm not sure you'd like that breakdown, but I feel like the places that have high nutrient runoff aren't the same as the places that have high sediment runoff. So that's my first distinction. The toss-up for me would be between trying to figure out whether Mauna Loa Bay or Waikiki would have the highest impact, but both of them really receive the most amount of human-induced pollution, and both are entirely channelized, and so there's so much impervious surface that it all moves to the coast pretty quickly. So I probably would prioritize those two bays, and I'm not sure the way that each of them is engineered is very different, right? One into a concentrated system in the Alawai versus one that's a little bit more distributed. In Mauna Loa Bay, you have, I think, 8 watersheds that are moving different amounts of stormwater into different places, and so it would require 8 separate systems of management. Whereas the Alawai would be able to be treated as one big whole unit. The other 2 places that come to mind are the tippy tops in Haleiwa and Pearl Harbor at the top and bottom of Waikele and I'm trying to remember the name. Yeah, exactly. So both below Wahiwa Reservoir. Wahiwa Reservoir right now is serving an enormous purpose of actually collecting sediment and all of the runoff from the mountains, but being able to have a similar system of collection down below that. There's a lot of sediment there. And then in Pearl Harbor would be the 2 highest sediment spots on Oahu. I'm not sure if that answers your question, but Alawai and Mauna Loa Bay are really kind of the hot targets for, I think, figuring out how to slow water down as it gets to the coast. Yes.
In your Lanikai study, you were mentioning that you had high bacterial counts on either end. Lanikai has no public restrooms.
They don't. I love this question. I love this question.
Okay.
It's my favorite question. I always have it. Give me a second. It was hiding in here too. You see the 4% here in the nitrogen source? So I went through and I asked and I made some really wonderful gross assumptions using FAO data on how much people go to the bathroom when they go to the beach and what % of the time they're going to go in the water, right? And then I added it all up and I added the amount of nitrogen that possibly came from that source. and I threw it into my pie graph so I can answer your question. Right now, from a nitrogen perspective, it's very small. The places I found had bacterial loads were at the two edges where very few people go at Lanikai, and then I call it Beach Access 1 because I can never remember the name. The first street when you come into the left in Lanikai, the very first beach access there. My estimate is that because it was, that there was some amount of sand remaining in the samples for just a little bit amount of time, and that the Enterococcus like to bind onto the sand, that there, whatever amount of Enterococcus is in the water were able to bind onto the sand particles in those two samples. So that was our first estimate, but definitely if there is somebody who wants to go out and try to figure out how to continue this just a little more to keep testing Enterococcus on the two edges, I'd be interested in seeing what those data were. Of note, when you come into Lanikai on the left there, the stormwater system, the wastewater system, nothing in Lanikai is on cesspool, nothing. Everybody is on sewer. And so there is the sewer line literally touches the water almost on that first beach access. You can come and you can see the manhole cover. And there are places, our infrastructure isn't all that great, right? Where sewer infrastructure has broken down and it does leak, it does have saltwater intrusion. So it would be interesting to check that site two more times and to try to see if you can work with the city just to make sure that that particular part of the infrastructure isn't degraded. But yeah, I did. It might be ridiculous, but I get the question all the time, so I added it in. Question.
So we talked about sediment and Enterococcus as being non-point source pollutants. Does salt water along the coast serve as suitable habitat for it to reside or propagate so that it becomes a point source, or should it be dissipating if we can cut off the non-point source upstream? Yeah,
our saving grace here in Hawaii is that a lot of the bacteria hit salt water, and I don't think they can survive very well in salt water. I do believe it is a saving grace for the health of our waters. That the reason more people aren't getting sick, in my opinion, is because they're hitting the salt. And so it is a poor indicator in salt water, but it is what we got.
Are brackish wetlands a different story, or
brackish
because of the dilution factor?
Yes, I would expect that the values would be very different in brackish, but perhaps the bacterial side isn't I don't do as much microbial as I do the sediment nutrients, but my understanding is that first off, Enterococcus is a poor indicator because both humans and animals can contribute to Enterococcus numbers, and so it's hard to separate. My understanding is in Kauai and Hanalei watershed, they spent a whole lot of time trying to track the Hanalei watershed sources of Enterococcus, and that in the end, a lot of it was sourced from pigs, that a good portion of it. So when you see high Enterococcus numbers associated with groundwater, it doesn't just mean human, but it can also mean human and pig fecal matter since our percentage of pigs is so high. So just something to think about. But in wetlands, yeah, those bacteria are going to probably survive a lot better in freshwater systems. So I did not go through the exercise of adding up pig poop in this particular model, but I have. So if you need to know for cattle or for pigs or for goats, I have done watershed models that add that up and try to add that as a nitrogen source. Yes.
Precipitation and storm events are major drivers for downstream effects.
Yeah.
And it focused a lot on West Maui, which is generally the drier side. So it's,
yeah.
Anyways, I don't know where I'm going with this, but would you expect, is pollution, non-point source pollution, more severe on wetter locations, or is it actually drier locations that are picked up in the storm events?
Good question. They're so different. So what I did not mention in this whole talk is that a good portion of my time right now is happening in Pae Āina wetlands, which is what Jesse talked about last week. He talked about the HCDA lands. So I actually spend a good portion of my time on the windward side now, analyzing windward data and doing all of that. My colleague, Lanikai Schultz, is coming to talk about the project in a couple weeks. So I let him take all the glory for the wetlands project. But I do spend a lot of time on the windward side now. And one observation is that because of the way the winds are, the mixing factor on the windward side is a lot higher. And so even if you did have more, the the mixing actually can reduce the impact a little bit compared to West Maui. And that in the leeward sides, that everything is coming down in these 4 events per year, right? It's all just concentrated into these events. And these days, some of those events are happening more frequently, but in general, because of that, you get that first flush effect every time. And so that when you do have an event, it's moving things, just moving things in a big hit, as opposed to the windward side, which is flushing itself a little bit more frequently. So maybe total load numbers would be equal based on land use, equal per hectare in both places, but that the fact that you have it more constantly exported on the windward side might mean that the effect might be a little diluted.
Kim, are you going to be around for a few minutes if people have further questions? Okay. Thank you again so much for a great presentation.
Thank you, Melissa.